Okay, great. Thanks very much for inviting me. I'm sorry I couldn't make it all the way to Glasgow. Christina is there though, so any questions you have after the talk, because later on she can certainly field. So it's about our paper, Structured versus Decorated Cospans with Kenny Corser as well. So a question that's been on my mind for the last decade is, can mathematicians do anything to help humanity deal with a climate crisis? As you know, Europe is now in its worst heat wave for the last 200 years. But the real issue is that this is just the beginning of a much worse set of situations. This heat wave will someday be regarded as normal, and then there will be new heat waves, which are much worse than that. And so one thing that category theorists can do is to better understand networks and open systems. So life can be thought of as a very complex, hierarchical set of networks of various kinds, some rather concrete, like the veins in a leaf, many others more abstract. And these networks are ways of organizing open systems. So in thermodynamics and other subjects, an open system can be thought of as one that interacts with its surroundings. There's some type of boundary demarcating the edge of the open system, and stuff of various sorts, information, matter, energy, etc., can flow in or out through the boundary. This is a very abstract bunch of concepts, and so that's why category theorists might be able to help understand it, because we're good at abstraction. So I was thinking about this, and I decided we should start with some rather simple examples, like electrical circuits. So your house and mine is full of electrical circuits, but you can think of open electrical circuits, that is, circuits that have some loose ends, getting them ready to hook up to other circuits. You can think of them as morphisms in a category, and sticking them together is composing them. And so a nice math question as a warm-up for all sorts of harder questions would be to describe the category of open electrical circuits, maybe just circuits with resistors, for example, as morphisms. So Brendan took a while to answer that question, but when he did, he answered a much better question. He came up with a general formalism for describing open systems called the theory of decorated cospans, which is part of what I want to explain today. Here's a picture. I was in Singapore at the time. Brendan first came as a kind of a visitor to the Center for Quantum Technologies where I was working. And that other guy on the left there is Blake Pollard, another student of mine who applied decorated cospans along with Brendan and me to another example, the example of Markov processes, open Markov processes. A lot of stuff happened. In 2018, Kenny Corser and I came up with another framework for describing open systems, rather similar, which we called structured cospans. And we did this because these are often simpler to work with than decorated cospans. And then Lina came to UC Riverside and helped us generalize the original theory of decorated cospans and relate it to the theory of structured cospans. Down at the bottom there are her funding agencies. And there's Christina and Kenny. So by now, structured and decorated cospans have been used to study and design also many different kinds of open systems. Open graphs are a mathematically simple example, and that's what I'll focus on just because they're easy. But more interesting ones for the purposes of applications are open Petri nets, which I worked on with Jade, open electrical circuits, open Markov processes, open dynamical systems, open Petri nets with rates, which are approximately the same thing as chemical reaction networks, and open stock flow diagrams, which I'll show you a picture of later. The last two are particularly exciting to me because those are open systems that have functors to the category of open dynamical systems. So they are ways of describing open dynamical systems. And they are both used now quite a lot in well, not only chemistry, but also epidemiology. So an interesting twist occurred in 2020 when Everett Patterson implemented structured cospans in algebraic Julia. There are a bunch of people working on algebraic Julia, the framework for doing category theoretic computation in Julia, which is a programming language that's supposed to be good for high-powered scientific computation. And using this system, those open Petri nets with rates, James Fairbanks and Mika Halter reconstructed some of a COVID-19 model used by the UK government. Here's a portion of this model, and this is a picture of a Petri net with rates. So this got a bunch of people excited that maybe you could use the structured cospan mathematics to actually do quite practical things. And a bunch of epidemiologists started talking to us. In 2022, Sophie Libkind, Andrew Baez, Mika Halter, and Evan Patterson, and James Fairbanks used algebraic Julia to build various models of epidemiology using open Petri nets with rates. Here, some of them are shown being composed, but they also used pullbacks and other category theoretic tricks to design big open Petri nets with rates. They have a nice paper about that. And then later, my old friend Nate Osgood and his grad student Xiaoyan Li joined the gang and really bumped it up to a higher level because they happened to be in charge of COVID modeling for the Canadian government. So they have hands-on, routine, day-to-day experience with epidemiology models. And they were the ones who argued that we should focus on open stock flow diagrams, which is a framework for modeling how entities of various kinds living in these boxes, these colored boxes called stocks, can move or along these double-edged arrows called flows from one box to another. So for example, sick patients can recover and so on. And these stock flow diagrams give you a way of describing sets of differential equations that describe the time evolution of such systems. And these are widely used by epidemiologists. But the existing software packages for working with these are not fully compositional in that what we can't do with the existing software is I build a model and then you somewhere else build a model, and then later we compose our models to form a bigger model. This is exactly what structured and decorated cospans are good for. And now we have software that does it. And in my talk on Friday, I'll talk more about that and the practicalities of that. But now I want to turn to the math of structured and decorated cospans so that you get an idea of what's really going on here. So I'm going to use the example of open graphs a whole lot. So here's a picture of an open graph. There's an input set A, an output set B, and maps from both those sets into the set of nodes of the graph. So N1 through N4 are called nodes of the graph, and then there are also edges of the graph. So what we have here is an open system of a very rudimentary sort, namely this open graph. So it consists of a graph, but it also has a kind of boundary or interfaces, namely these input and output sets A. And the point is that why work with open graphs? Well, because that's a nice way to describe how to build big graphs out of smaller ones. You can compose open graphs by gluing them end to end. So if the output set of one matches the input set of the other, you can identify them. So identify each node in the first graph with each node in the second graph if they're mapped to by the same element of B. And so you're really doing a push out there when you're sticking them together that way, and you get a bigger open graph. So it's a very intuitive process, just sticking things together. Now this composition, it's associative only up to isomorphism, because when you do a push out of graphs, you have to make up your mind how you're going to name these new elements, these new nodes. And if I call them X and X prime and you called them Y and Y prime, then your composite would just be isomorphic to mine. So if we pick a composite, just randomly pick one way to do it, that's fine and dandy, but then composition will be associative only up to isomorphism. But then that raises the question, what do we mean by isomorphism? I mean, it's sort of intuitively obvious that if I just relabeled these nodes something else, we'd get an isomorphic open graph. That's the intuition behind it. But we have to understand what category we're talking about when we talk about things being isomorphic. So the point is, there really is a category of open graphs. For example, there's a morphism from this open graph to this other open graph. Notice these actually have different, potentially different source and target sets. So what we have here is a map from A to A prime, where the points 1 and 2 are both getting mapped to the point 1 prime, and 3 is getting mapped to 3 prime. We've got a map from B to B prime that does the only thing it can. We've got a map here from this graph to this graph. So that's a map sending nodes to nodes, edges to edges, and preserving the property that preserving the structure that every edge has a source and target node. So like these two edges here are getting mapped down to one edge, and we can also map a graph into a larger graph that has extra nodes and edges. So there's a category of all open graphs, and that allows us to define this concept of isomorphism that we need for me to make sense of the idea that composition is associative up to isomorphism. So what we've got is the structure that sounds a little Baroque if you've never seen it before, but it's actually very familiar if you, after a while, you see it showing up all over the place. There are morphisms between open graphs, and composition of those morphisms is associative, but then open graphs are themselves morphisms. You can compose them, and that's associative up to isomorphism. So the structure that captures those two forms of composition is called a double category. So a double category has figures like this. They look like squares. So it has objects A, B, C, and D, and then it has vertical one morphisms, such as F and G here. Those were the functions between sets in our open graph example. But then it also has horizontal things, which I'll call one cells to distinguish them a little bit more from the vertical one morphisms. Those would be the open graphs themselves in our example. And then it has these two-dimensional things, which I'll call two morphisms, which would be a map of open graphs. In our example, would be a map of open graphs, sending this open graph to that open graph. So you can compose vertical one morphisms, and you can compose horizontal one cells. You can compose two morphisms, both vertically and horizontally. The interchange law holds that says that when you compose these two vertically and these two vertically, and then compose the results horizontally, it's the same as if you did it the other way around. That is, compose these horizontally, those horizontally, and then the whole thing vertically. Vertical composition is strictly associative and unital. Horizontal composition is only associative and unital up to isomorphism. That's a mouthful. We can certainly summarize that or state that much more efficiently using a bit more category theory, but that's the idea of a double category. So the question is, how do you get the double category of open graphs? And the key, which will lead us to handle many more examples, is to realize that an open graph is, for starters, a cospan of sets, where n is the set of nodes of the graph. But where the apex of the cospan, that is the set of nodes, is equipped with some extra structure, namely in the structure in this case of being the nodes of a graph. So we have not just a cospan of sets, but a cospan where the apex has some extra bells and whistles attached to it. And what is it? Well, it has the structure of a graph on n. So given a set n, a graph on n is a set of edges, and then two functions assigning the source and target of each edge to some node. So then an open graph is a cospan of sets together with a graph on n. So that's the paradigm of both structured and decorated cospans, is that you have a cospan, but then together with some extra structure on the apex. So how do you frame that in a general context? So there are actually two ways that we know of to equip an object of a category with extra data. So one, just for the purposes of this talk and for the term structured cospan, I'll call structuring. So the idea is that if you have a right adjoint functor, think of it as some kind of forgetful functor, you can give an object of A some extra structure by choosing an object of X that maps to it. So, putting a group structure on a set would be done in that way typically. But then there's another method which we're going to call decorating, which is that if you have some sort of map from your category A to cat, then for each object of A, you get a category f of A, and then you can decorate that object of A with an object of that category. So I want to develop both approaches and then relate them. So let's do decorating. I'm going to do that because it's harder. I've learned through many years of giving talks that people are less tired at the beginning of the talk, so you should actually do the harder stuff first, counterintuitively. So let's do the example of open graphs as a decorated cospan category. Okay, so for any finite set n, there's a category f of n of graphs on n. So here our set n is the nodes n1 through n4. Here are two different graphs, and here's a map of graphs that preserves the nodes, but can do interesting things with the edges. So it's a morphism in this category f of n. So these are graphs with a fixed set of nodes where the morphisms don't do anything to the nodes. Now, there's actually a way to assign to any finite set. Sorry, I should have said set here, not fin set. I was vacillating whether I should keep things finite or not, but I'm actually going to do all sets. So there's a map assigning to any set a category, which is the category of graphs on that set. But what kind of map is this? Well, it turns out to be a Lax-monoidal pseudofunctor. That's a little bit of a jawbreaker at first. Pseudofunctor means that composition is that f preserves composition only up to a specified isomorphism that needs to satisfy some laws. We're not going to worry about that a whole lot, actually, because of shortage of time. But the interesting thing is the Lax-monoidal part, namely that our functor preserves the monoidal structure up to a morphism. The monoidal structure on sets that I'm going to use is union or plus. The monoidal structure on cat that I'm going to use is Cartesian product. And so what I'm saying here is that if I take a graph on n and a graph on m, I can combine them to get a graph on the disjoint union of the sets n and m. And the way we do it is just the visually obvious way. Here's a graph on n, here's a graph on m. I just set them side by side and get a graph on n plus m. So we get this map phi, which I'll call the laxator, and it's lax. It's not an isomorphism because there are also lots of other graphs on the set n plus m besides the ones that fall apart neatly into these two pieces. So this is not an isomorphism. So in general, it turns out that given a Lax-monoidal pseudofunctor, you can define a decorated cospan, which is a cospan in A where the apex is equipped with the decoration in f of n, where n is that apex. So open graphs are decorated cospans where A is the category set and f maps any set to the category of graphs on that set. And then the idea is that you can compose decorated cospans. So if I have one here and another one there, where the second one starts where the first one left off, you can compose them. So you first take the two cospans, which I draw down here, and you do a push out of them. You can always think of a push out as first doing a coproduct and then a co-equalizer. And we think of it that sort of fancy way because we want to figure out how the decoration on n and the decoration on m combine to give a decoration on this push out. And so here's how it works. First, you use the laxator to take those two decorations and to turn it into a decoration on the disjoint union n plus m. And then, given that f is a functor, or at least a pseudofunctor, we can use this map C here and take f of C, and that will carry our decoration from the disjoint union to this push out. And so you can, that's the key thing, that this Lax-monoidality of f is what lets you compose decorated cospans and know how to deal with the decorations. So Kenny and Christina and I proved this theorem, which is a sort of souped up version of Brendan's original decorated cospan construction. So it says, suppose you have any category A that has finite colimits, and suppose you have Lax-monoidal pseudofunctors of the sort I've just been talking about, then you get a decorated cospan double category. So the objects will be the objects of A, the vertical morphisms will just be the morphisms in A, the horizontal one cells are going to be the decorated cospans, where the decorations make use of this functor F, and then a two morphism will be a commuting diagram in A together with a decoration morphism. So So we have this decoration in f of n, and we can apply f of h to it to get a decoration in f of n prime. So these are both decorations in f of n prime, and we want a decoration morphism going from one to the other. In our example of open graphs, that would just be the sort of obvious kind of map of graphs that you need to map one open graph to another open graph. But there's a little bit more. In fact, you can tensor open graphs. If I have an open graph and another open graph, I can just set them side by side or one on top of the other in this picture. And that takes advantage of the coproducts in the category A. And so that's going to give some kind of symmetric monoidal structure to our decorated cospan double category. And so there's a souped up version of our result that handles that, which says that if you have the same hypotheses, but f here is a symmetric lax monoidal pseudofunctor, so that's the only additional hypothesis, then the decorated cospan double category we get is symmetric monoidal. I will spare you the definition of a symmetric monoidal double category because it's a little complicated, but it just means that you can tensor objects and all the various kinds of morphisms. Okay, so that was decorated cospans. It turns out that structured cospans are somewhat simpler when they actually work. And so remember, structuring is a different way of giving an object in A some extra structure. Namely, you pick a right adjoint functor from some other category X to A. So think of this as like the forgetful functor from graphs to sets. I have a set, I want to give it some extra structure, so I pick a graph whose underlying set of nodes is my set. So that's how structured cospans work. A structured cospan will be a cospan in A, but where the apex is of the form R of some object in the category X. So you should think of A as the category of objects with less structure. They form the boundary of our open system, boundaries of our open systems, and X as a category of objects with more structure. So this is how it works in the case of open graphs here. R is the forgetful functor from graphs to sets. It picks out the nodes. But the interesting thing is that, of course, whenever you have a right adjoint, you have a left adjoint. So you also get a left adjoint going from A back to X. So using the adjointness property, you can reinterpret the structured cospan as a diagram in X going from the left adjoint applied to the feet into the apex. And this other way of thinking about it turns out to be a little bit more practical. And in particular, you can compose structured cospans simply by doing pushouts in the category X. We have to assume that category has pushouts to do that, but then it's nice and easy. So none of this fancy stuff about how you compose the decorations, which we had to do in the decorated cospan approach. So in our running example here, A is the category of sets, X is the category of graphs, and L of A, where A is some set, would be the graph with A as its set of nodes and no edges. That's the free graph. So you can think of these open graphs as in this funny way where you take these two sets here and you just turn them into graphs without any edges, and you just map them into this interesting graph here on the apex. So first, Kenny and I, and then Kenny and Christina and I proved a theorem about how to get structured cospan double categories. The second proof is much more slick and nice. So here we'll assume that both A and X have finite colimits. So remember, that means having pushouts and also coproducts, finite coproducts. And you have a left adjoint functor from A to X. Then you get a structured cospan double category. So the objects are objects of A, as in the previous theorem that looks similar to this. The vertical morphisms are morphisms in A. The horizontal one cells are now the structured cospans, and the two morphisms are just commuting diagrams. All this is happening in the category X. And notice that here we automatically get symmetric monoidal as part of the result. So structured cospans are simpler, but unfortunately, not all decorated cospans can be seen as structured cospans. So initially I was hoping to get rid of the decorated cospans and just use structured ones, but it turns out that when we start doing applications, we encounter interesting examples where you need, apparently, we need to use decorated cospans. In particular, open dynamical systems, which I won't really get into here, but I will a bit on Friday, seem to need decorated cospans. And the key is that the forgetful functor from dynamical systems to finite sets has no left adjoint, which Kenny and Christina and I showed. So why I said that it seems that this is true is that there might be some sneaky trick where you change your definition of the category of open dynamical systems or something, and maybe you could wriggle out of this problem, but we don't know how to do that yet. So this is theoretically interesting, but it's also practically important because over in algebraic Julia, various people have set up ways of manipulating and manipulating structured cospans. They can also do decorated cospans, but there's been more work on structured cospans. So it's now sort of a pressing issue, like, oh, how much do we need to develop the decorated cospan framework to do the practical things that we want to do, like fight disease and save the world. So this raises the question, for example, when can you take a decorated cospan category and see it as a structured cospan category? So of course, to do that, you have to relate the key ingredient for decorated cospans, which is this lax monoidal pseudo-functor from A to cat, to the key ingredient for the structured cospan category, which was this right adjoint functor from some category X to A. Now, if you stare at these two items and you think about it a while and you know some category theory, you should be reminded of the Grothendieck construction, because the Grothendieck construction is a trick for saying that whenever you have any pseudo-functor from a category to cat, you can build a new category called the integral of F, and that category comes with a functor back down to A. And it's not just any old functor, it's an especially nice kind called an op vibration. And in fact, like in our example of where R is the functor from graphs to sets, that is indeed an op vibration. And what that means, I won't go into the details of what op vibrations are, but what it means is that if I have a set with a graph on it, and then I have a map from that set to some other set, then I can carry that graph along that map and get a graph on the other set. So I can lift morphisms in A to morphisms in X in a nice way. That's the idea of an op vibration, a rough idea. So that's what you get for free whenever you have any pseudo-functor from A to cat. But we're assuming more when we're working with decorated cospans. We're assuming that F is a symmetric lax monoidal pseudo-functor, and we want more for structured cospans. We want R to be a right adjoint. The Grothendieck construction doesn't ensure that you get a right adjoint all the time. So we need to work a bit more. Well, luckily, Mike Schulman and also my former grad student, Joe Moeller, who's also there, I believe, and Christina Vasilikopoulou, proved just what we need, which is a relationship that deals with these extra complications in the Grothendieck construction. So if A is a category of finite coproducts, these three different items correspond to each other. One is symmetric lax monoidal pseudofunctors from A with its coproduct monoidal structure to cat with its product monoidal structure. The next one is pseudofunctors from A to Simon cat. So in other words, you can think of F as assigning not just a category to any object, but a symmetric monoidal category. And third, symmetric monoidal op vibrations from X, this category you build from the Grothendieck construction, to A. So let me illustrate these things in our running example. So if A is set and F is the pseudo-functor sending any set to the category of graphs on it, I've already mentioned that it's lax symmetric monoidal, where the laxator sends any pair of graphs to the disjoint union. So that's one way to think about it. But in fact, each of these categories, F of n, has finite colimits, and thus it becomes symmetric monoidal using coproduct. So our pseudo-functor f can actually be thought of as a pseudo-functor from A to Simon cat. And now another thing that you notice here, which we're going to need in a second, is that f factors through Rex, the king of all categories. Now, Rex is the 2 category of categories with finite colimits. Rex stands for right exact, actually. So what I'm trying to say here is that the f of n is not just any old symmetric monoidal category. It's actually a category with finite colimits where the symmetric monoidal structure is coproduct. So it's an object in Rex, not just in Simon cat. And then the third point of view is that if you do the growth and deconstruction to this f, you get the category of graphs, and then the forgetful functor back down to sets is actually a symmetric monoidal op vibration. So these are the 3 different viewpoints on the same idea that are stated to be equivalent in these results of my friends and co-authors. So using that nice result, we were able to, both state and also help prove this theorem. So suppose you've got A with finite colimits and you have a symmetric lax monoidal pseudofunctor. That's just the junk you need to get a decorated cospan double category. But now, so by the result I just mentioned, that means you get a pseudofunctor from A to Simon cat. And now make an extra assumption. Suppose it factors through Rex. Suppose that the symmetric monoidal categories you get are actually categories with finite colimits. So then the symmetric monoidal double categories of decorated cospans and structured cospans both make sense, and they are in fact isomorphic. The decorated cospan category, double category you get just because you have this F here. The structured cospan one, what you have to do to get a hold of that is you do the growth and deconstruction, op vibration, but then using the extra hypotheses, one can show, and this is like the work, that this actually has a left adjoint. So now you have this left adjoint, and then that's, in other words, you show that R is a right adjoint, so that it has a left adjoint, and so you can define structured cospans. And then you still have to work further to actually prove that these 2 symmetric monoidal double categories are actually equivalent. In fact, isomorphic, for a strong sense of equivalence. So that handles our case of open graphs, and it handles all the cases we know where you can describe the same situation using both structured or decorated cospans. So there are some open problems I'd like to end up with, to leave off with here. So there's the reverse question: when are decorated cospan double categories also structured cospan categories, going back? So actually, Daniel Sakala and Christina know a lot about this. So what I'm doing right now is I'm pressuring them to write their paper about this. This is a public pressure campaign to get this paper written. But we don't even with that, there are other wonderful results that they're going to write up. We haven't gotten like a necessary and sufficient conditions for when structured and decorated cospans are equivalent, I think. And then there's another twist. Sometimes even when they're not equivalent, the decorated, even when a decorated cospan double category is not equivalent to a structured cospan double category at the double category level, sometimes the corresponding categories actually are. That actually shows up for things like open Petri nets with rates. And so that's of practical importance. Well, when does it happen? Examples where it happens. And a bigger open problem is, can we develop some sort of taxonomy of the useful structured and decorated cospan double categories and maps between them? The maps between them are how we implement some different sorts of semantics of our open system modeling frameworks. So to understand this would really be developing a general theory of open systems and how you can, the syntax and semantics for them. That's sort of an open question there. That's not a very precise question at present, but there should be something general one can say about this. And finally, will someone create software that will do practical things, not just with the categories of structured and decorated cospans, which most of the work has been using just that, but also the double category. In fact, some of the work has been using the double category structure because people have been refining disease models using pullbacks, and those are pullbacks in the categories of the vertical morphisms. And so the double category approach is actually already showing up in practical context, but the software doesn't really fully reflect the double category framework. So there's a lot left to do there. Okay, thanks very much. That's it.
Thank you very much. Are there any questions in the audience? Yeah.
Can you say more about why you think a taxonomy of the useful structure decorated for simple categories would be like universal language?
I didn't hear the last little end. Why it would be
a universal language in open systems?
Well, I'm exaggerating a little bit. Oh, I mean, open systems is a very general concept. So, but the point is that many different types of open systems have been described using structured and decorated cospans, and we're really just getting started. These are just some examples. I can easily crank them out. Basically, almost any language of diagrams, like electrical circuits or and many other diagrams, gives rise to a structured or decorated cospan double category. And these languages are used in different branches of science and engineering, electrical engineering, biology, genetics, and so on. And they keep, I suspect that there's like a general story of these different structured and decorated cospan categories, which are the ones that people actually need in biology and chemistry and engineering and so on, that they're not the arbitrary ones, there's something special about them. And so you could say it might be a bit like we've discovered 9 or 10 different groups, and we've discovered that like groups are cool, but we don't have like a theory of groups. And so we don't really know, like, why do we like these particular groups better than some other groups? So I think there's a lot left to understand there.
Any more questions? Oh. Someone want to read it?
Yeah. Someone in the chat is saying, in my 2002
I'm afraid you'll have to speak up, or else Jade will have to repeat the question.
can you hear me?
Now, yes.
Okay. So in the chat, someone is asking, in my 2002 PhD thesis under Luke Kaufman, I deal with decorated convection graphs being algorithmically aligned in order to properly structure them. It seems that your problem is directly a categorical version of this.
That's interesting. What type of graphs did you say those were? I didn't quite catch that key word there, but I'll have to look into it.
Contraction graphs.
Okay. I don't know about those, so I'll have to look at those. Yeah. There should be lots of beautiful pure math examples of these categories as well. I've been sort of trying to focus in on the more applied math examples.
This was a question from Fernando Souza.
Yeah. Okay. Yeah. I'll check it out.
Yeah. Thanks.
Thanks.
So someone asked if feedback arrows are admitted, and yeah, self loops are admitted in those graphs. Okay. I can't look at the audience and see that they're like getting ready to move on. So
thanks for your awareness. So I want to ask, because you mentioned that you can always apply the algorithmic structure, except what you get isn't always the right answer, so you cannot always do structure constants. What I was curious about is the symmetric model actually good enough to work with? So could you instead weaken your assumption of a structure, Cospans, or would you lose all the simplicity that you get from the right answer to weaken the model application?
There might be something you could do, but as you guessed, that would sort of it would reduce the simplicity of the situation. So the fact that our forgetful functor R is a right adjoint lets us flip it around and think of it as think in terms of the left adjoint, and then composing the structured cospans is just as simple as composing diagrams, composing cospans in X. So we've sort of reduced the structured cospans to a special class of cospans. And so if you didn't have this left and right adjoint, then that wouldn't work. Now, it's still possible that maybe you could work with a different monoidal structure other than the co-limits or coproduct monoidal structure. So we are also getting that benefit from our theorem, is that that we had a monoidal structure of a special sort. So there might be some intermediate case where you have this right adjoint, but you should think of A and X as symmetric monoidal rather than using coproducts. But I haven't really thought about that, so that could be interesting.
Okay, thank you very much. Maybe
Great.
one more round of applause.